This is solubility and intermolecular forces for AP chemistry. We're going to first look at some definitions. Solution means that you have a homogeneous mixture. Solvent is the major component. Solute is your minor component. If we have miscible liquids, that means that they dissolve completely in each other in any proportion. It sounds kind of like saying mixable. Immiscible means that the liquids are insoluble in each other and they form separate layers. For example, this could be oil floating on top of water, and we know that those two layers will not mix. Let's take a look at what happens as we dissolve substances in each other. And it really all comes down to looking at what's going on with the intermolecular forces. So step one, we need to overcome the intermolecular forces between the solvent molecules. So this first step, we overcome IMFs. In the second step, we're going to overcome the IMFs between the solute particles. Both of these are endothermic processes. We have to put energy in to overcome IMFs. When we get to step 3, now we're going to be forming new attractions between all of the various solute and solvent particles. And so we're going to get energy back. And so this final step is exothermic. Let's take a look at this from an energy diagram standpoint. So here we have our step 1, where we are overcoming IMFs. Step 2, we are overcoming IMFs. Step 3, now we're forming new IMFs. And so we're going to get energy back. Since we get more energy back than we originally put in, this is an exothermic process. An example of this is dissolving calcium chloride in water. We generate heat and the solution will warm up. Now let's take a look at a similar process. Again, we put in energy to overcome IMFs. We put in energy to overcome IMFs. Then as the new intermolecular attractions form between solute and solvent, we get energy back. But this time we did not get as much energy back. So now we have an endothermic process. So an example of this is dissolving ammonium chloride in water. In this case, the solution gets colder as heat is absorbed from the water. How do we predict if something is soluble or miscible? Well, again, it all depends on the intermolecular forces. There's a phrase, like dissolves like. Substances dissolve in each other when the substances have similar intermolecular forces. Polar compounds dissolve polar compounds. Nonpolar compounds dissolve nonpolar compounds. Now, an example of nonpolar compounds dissolving nonpolar compounds would be a method of getting gum out of hair. So, peanut butter is nonpolar, gum is nonpolar. So if you get gum in your hair, you mush the peanut butter through your hair, and then you take a shower and shampoo the gummy peanut butter mix out. Let's do a little review here on intermolecular forces and solubility. So if we have similar IMF interactions between solute and solvent particles, they will be soluble in each other. So here's an example of methanol and H2O. Both are capable of hydrogen bonding, so they hydrogen bond in solution. Here we have two polar molecules, ethanol and chloroform. So we're going to have dipole-dipole attractions. Now, we'll also have London dispersion forces. And then this last one, we have two nonpolar molecules. They cannot have dipole-dipole attractions. The only thing they can have is dispersion forces attracting them together. Let's take a look at compounds that are soluble in water. We know water molecules form intermolecular hydrogen bonds with each other, but they will also form intermolecular hydrogen bonds with solute molecules that contain HN, HO, or HF bonds, the phrase HNOF. So H has to be directly bonded to either N, O, or F. So here's an AP type question. Draw one water molecule interacting with ethanol, and there's actually two possible answers. So first of all, let's put the lone pairs in here. And first we'll show a water molecule interacting with the lone pair on the oxygen. So that is one possible answer. Now we also could show this hydrogen molecule or atom interacting with a water molecule on, or with a hydrogen on the other molecule. Let me erase this here because I don't actually like the way I drew this. So I'm erasing that because I didn't show the actual hydrogen bond. So let me do that again. So I would show hydrogen, oxygen, hydrogen, and I need to show the actual intermolecular hydrogen bond. So that's your IHB, IHB. So each of these answers is correct. You only need to draw one. So let's take a look at how the solubility of different size alcohols. We're first going to look at small alcohols. So ethanol is C2H5OH, okay? So the water molecules are held together by intermolecular hydrogen bonds, as are the ethanol molecules. So we have to overcome the hydrogen bonds between the water. Then we're going to form a solution and we're going to set up new intermolecular hydrogen bonds. The energy released is about the same that was needed to break the original intermolecular hydrogen interactions. However, let's see what happens when we use larger molecules. So for example, pentanol, which is C5H11OH, we still can form intermolecular hydrogen bondings, but now we have this big, long, nonpolar tail. And so this nonpolar tail part is not soluble in water. So that means that as we make the chain longer and longer, the solubility of the larger alcohols goes down. This is an image of mixing a nonpolar and a polar substance. On the top we have hexane, which is nonpolar. And on the bottom we have water, which can form the intermolecular hydrogen bonding. Notice they do not mix appreciably. The polar molecules attract each other strongly. Now, the molecules also attract the nonpolar hexane by something called dipole-induced dipole attractions, and we'll talk about that on the next slide. However, the water molecules are more attracted to each other, and they actually exclude the nonpolar hexane. So the water molecules would prefer to adhere to each other than to adhere to the hexane. You can have solubility when you have different types of IMFs, but the solubility is going to be different. So let's take a look at some possible intermolecular forces interactions between solute and solvent properties. The first one is ion-dipole interactions. Ionic compounds can be very soluble in water due to this. The next one is dipole-induced dipole, which we talked about on the previous slide. If you have a polar molecule like acetone approaching a nonpolar molecule, it will actually induce a positive and negative end on it. So this is induced and it is temporary. So it's not a very strong attraction. So polar and nonpolar compounds will only be slightly soluble in each other. You can also have ion-induced dipole. So the chlorine ion here has a negative charge and it will induce, again, a temporary dipole. Now this is not very strong. So again, they'll be very slightly soluble in nonpolar compounds. Let's take a deeper look at the solubility of ionic compounds in water. So water molecules are obviously polar. As the ions are solvated, you're going to have the negative end of the water molecule being attracted to the positive cations, and the positive end of the water molecule being attracted to the negative anions. We can use Coulomb's law up here. Force is proportional to the charge. Remember, Q is the charge, and D is your distance. So the more highly charged the ion, the more strongly attracted the water molecules will be by ion dipole attractions. And this will be greater than if we have large low charged ions. However, the small highly charged ions are also going to be more attracted to each other by lattice energy. Okay, let's look at some sample AP questions from the AP classroom. So I'll just read these to you. The survival of aquatic organisms depends on the small amount of O2 that dissolves in H2O. The diagrams above represent possible models to explain this phenomena. Which diagram better provides the better particle representation for the solubility of O2 in H2O? Well, let's first take a look at what we know about O2. This is a nonpolar molecule. Okay? It does not have an H attached to an N, O, or F, so it is not capable of hydrogen bonding. So this is not a good drawing here, so we can cross out A and B. Now it says diagram 2, because the H2O molecule can temporarily induce dipoles on the electron cloud of O2. Okay, so that would be this drawing here, and that sounds reasonable. Let's take a look at negative one, or the D, because the nonpolar O2 can induce temporary dipoles on the electron clouds of H2O. Well, this is backwards, okay? This is the correct one here. Okay, next question. Benzene C6H6 has the structure shown above. Considering the observations that benzene is only sparingly soluble in water, which of the following best describes the intermolecular forces of attraction between water and benzene? So they're saying there is an attraction. First, benzene is nonpolar because there are no forces between water and benzene. Well, they've just told us there's a force of attraction, so let's cross this one out. The H atoms in benzene form hydrogen bonds with oxygen atoms in water. That doesn't work because we do not have any H, N, O, or F bonds. Okay, so we don't have any of those. That's not true. Benzene is hydrophobic, therefore there is a net repulsion between water and molecules. Well, they just told us to look for what's going on between them, and that is an attraction. And then we have there are dipole-induced dipole and London dispersion interactions between water and molecules, water and benzene. So we know they both got London dispersion interactions. They both have electron clouds, and water's polar, so it is going to induce a dipole. So it looks like our right answer should be D. All right, thank you very much.